The fading light of a flaring young star has shed light on a puzzle involving crystals and comets.
The Hidden Universe Showcase explores exciting new results in infrared astronomy from NASA's Spitzer Space Telescope, with your host, Dr. Robert Hurt.
For the most part, the universe changes very slowly compared to, well, us. The stars appear much the same to us today as they did to our ancestors. So, it's a rare treat when astronomers actually catch a star in the act of doing something unexpected, especially when it helps solve a long-standing puzzle. The star of this special event is about 500 light-years away and known as EX Lupi. It's probably a pretty close match to what our own sun was like in its infancy about 5 billion years ago. Early in 2008, it flared dramatically in brightness due to material from its disk falling onto the central star. The star's brightness increased by a factor of 100, heating the disk far from the star. It appears that tiny dust particles far out of the disk melted slightly, or annealed. As they cooled, they took on a new crystalline structure. This is the first time astronomers have ever caught crystals in the act of forming in a circumstellar disk. So, how is it possible to detect such tiny crystals around a star that is so far away? Well, dust is a specialty of NASA's Spitzer Space Telescope. Not only has Spitzer shown that dusty disks are common around young stars, its infrared spectrograph also allows us to study their compositions. By splitting its light up into a spectrum, astronomers can look for unique features, like spectral fingerprints, that correspond to specific minerals. This first observation of EX Lupi was made in 2005 and shows the signature of silicate minerals, which are pretty typical for dust. A second spectrum of this star, taken about 3 years later in 2008, shows a subtle but remarkable change. The extra bump comes from tiny olivine crystals mixed in with the dust, crystals that weren't there before. These crystals are known as forsterite, a form of the mineral olivine. Spitzer has seen this material in many places, surrounding young brown dwarfs too small to become stars, as well as white dwarf remnants of long-dead stars. It's even seen in the winds around supermassive black holes in the cores of distant galaxies. This discovery is remarkable because astronomers had never before witnessed such an ongoing chemical change in the disk around a young star. But it also solves a puzzle, not about distant stars and galaxies, but about comets right here in our own solar system. On July 4th, 2005, NASA's Deep Impact probe smashed into the comet Tempel 1. Spitzer's spectrograph observed the plume of ejected material and found the comet contained the same kind of crystalline olivine. This seemed odd because comets come from the cold recesses of the outer solar system. Crystalline olivine, however, requires high temperatures to form, presumably near the young sun. So, how did these crystals make it into comets that came from all the way out there? The forsterite forged around EX Lupi could solve the puzzle. These brilliant flare-ups in EX Lupi, which may happen every few decades, will heat up more distant parts of the disk. This would form the crystals in areas that would otherwise be too cold. If our own sun experienced similar flare-ups in its youth, which we think is the case, it could explain how forsterite ended up in comets like Tempel 1. Sometimes, a small wiggle in a spectral plot can tell a big story to the scientists who know how to read it. And sometimes, a discovery around a distant young star can tell a lot about what's happening right here in our own astronomical backyard. For the Spitzer Science Center, I'm Dr. Robert Hurt, reminding you there's a hidden universe just waiting to be discovered.
The Hidden Universe is produced by the Spitzer Science Center at the California Institute of Technology in Pasadena. The Spitzer mission is managed by NASA's Jet Propulsion Laboratory.